We'll start in this section with looking at t-tests. 6 total, 3 parametric, 3 non-parametric. The first one is here, the one mean t-test. Test if a sample mean is any different from a set value for a normally distributed value. For example, average body temperature from a set value. To do this, in G-Power, we start by selecting t-test from the test family, then means, difference from constant, one sample test from the statistical test, and of course, a priori. If you have background information, you can start by selecting one or two tails, then enter in the alpha or significance level of 0.05, followed by a 0.8 for power. To determine effect size, you can hit the determine box, enter in the mean of the null and alternative hypothesis, as well as standard deviation, hit calculate. It'll transfer to the main window, and you can hit calculate. This will give the total sample size. If you don't have any background information or naive, you can run A through C, but instead of hitting determine, just guess and enter in the effect size box. For t-test, a small effect is 0.2, a medium is 0.5, and a large is 0.8. And then hit calculate and you'll get total sample size. For the question, is the average body temperature of college students any different from 98.6? We find that the null would be that set value, 98.6, and the alternative is anything different. If you have trial data, you might find that the mean temperature for the alternative is 98.2 with a standard deviation of 0.733. For this, we want to select two-tailed because we're wondering if the temperature differs, not whether it's simply lower or simply higher. And we can enter in our means and standard deviation to get an effect size, which will give us a total sample size of 29. Here are 3 examples of one mean t-test exercises. I would highly suggest you pause this video and work through these yourselves before moving on to the answers. So you can pause now. All right, let's look at the answers. For the first one, average income of college freshmen, we're given the null and alternative hypothesis means and the standard deviation. You can just simply plug that in for an effect size of 0.91 and a one-tailed test to get a total sample size of 9. For the second, we're giving the raw data of sleep change, which we can use to get the mean of the alternative and the standard deviation to get effect size and a total sample size of 154. For question 3, we're giving no information, so we have to guess. So I guessed a large effect size and use a one-tailed test to get a total sample size of 12. I guessed a large effect because from anecdotal data, I know that students in college often have large weight changes their first year of college. The one mean Wilcoxon is the non-parametric analog to the one mean t-test. It's, again, testing if a sample mean is any different from a set value, but this is for non-normal data, like the average number of children in Grand Forks families. To do this, again, you select t-test, and now means Wilcoxon signed rank test. It's a one sample case, a priori. You'll select tails, but now, since it's non-parametric, you have to select a parent distribution. There's a Laplace logistic or min ARE. really depends on the variable. I will select the min-ARE as my default if I really don't know the distribution. It's the weakest, so it's the most conservative. It'll give you usually the highest sample size number, so you can be sure you cover it. You can enter your alpha and power. Then if you have background information, you can hit determine. And once again, add your means and standard deviations to calculate effect size and then get total sample size. Naive, as usual, you do A through D, but then just guess your effect size. For the question, is the average number of children in Grand Forks families greater than 1? Our null is 1 child. An alternative is anything greater than 1. I don't have background information, and I don't think it's normally distributed, so I'll use the Wilcoxon. I'll set one tail, because we're looking at greater than 1, and be conservative, so I'll use min-ARE. I think there's a good chance that a lot of families have more than 1 child, so I'll choose a large effect. And this gives me a total sample size of 13. Here are practice examples for the one mean Wilcoxon on average number of insurance claims, pets, and yearly trips to the emergency room. Again, I suggest you pause and practice on your own before looking at the answers. For number 1, we are given the means and standard deviation and the distribution, so we just plug these all in to get a total sample size of 39. For 2, we're given the raw data on pets. We can use that to get our alternative hypothesis means and standard deviation and get an effect size of 0.224. I don't know the distribution, so I'm going to go conservatively with min-ARE, get a total sample size of 145. The third, I'm giving no information, so I guess a medium effect, min-ARE, and use two-tailed to get a sample size of 39. Let's move on to two means. The two means t-test is very similar to the one means, but you're looking at the difference between two different means rather than one means and a set value. You can also think of this as testing to see if the difference between those two means is anything other than 0. For example, is the average body temperature higher in men than in women? To do this in G-power, t-test then means difference between two independent groups or two groups. Add your tails, alpha and power, but now you need to add a third, which is the allocation ratio. You can enter 1.0 if your group sizes are equal, but G-power can work with unequal group sizes, depending on if N2 and N1 are different, so the two group numbers. With background information, hit determination. Once again, means and standard deviation for each group. Calculate and get total sample size. Naive, A through D, and then guess effect size. Is the average body temperature higher in men than women? From a trial study, I find for men, it's 98.1 with a standard deviation and 98.4 for women with their own standard deviation. Since I only care if it's higher in men, I would select a one-tailed test here, and I would enter the means and standard deviation here. Since the group sizes I think would be the same, I'll enter a 1 here and get a total sample size of 146. You can see here that gives us the total sample size, and then for each group, the groups were equal, it's going to be the same number, 73 per gender. We have 3 practice examples here for 2 means: average daily caloric intake, average protein level in blood, and average glucose level in blood for men and women. Take some time to work on these on your own. Looking at the answers, first question, we're given both size, mean, and standard deviation. So I can plug in to get an effect size of 1.37. And now the allocation ratio is actually different than 1 because there is only 5 women and 10 men, so twice as many men as women, so the ratio is 0.5. And I get a total sample size of 22. And now we see here the sizes for men and women are different. Question 2, we're given the raw data with which we can get means, standard deviations for both groups, get an effect size from there. They're equal group sizes, so allocation ratio is 1 for a total sample size of 1560. The third question here gives no information other than that it's in a predominantly female college. So I'll guess a small effect with a two-tailed test. And now the allocation ratio I'll set is actually 3 because I expect I'd only be able to get like 1 man for every 3 women if it's mostly women. To get a total sample size of 826. A little over 200 men and over 600 women. The Mann-Whitney test is the 2-sample t-test analog for non-parametric data. Again, you can test to see if the difference in means is different from 0. To run this in G-Power, you'll have to have means, Wilcoxon, Mann-Whitney test, 2 groups. T-test a priori. Again, 1 and 2 tails. And like the 1 mean Wilcoxon, you have to select the parent distribution. And like the 2 means t-test, you'll have to select the allocation ratio. If you have background information, you can calculate effect size. If not, you can guess it. Does the average number of snacks per day for individuals on a diet differ between young and old persons? So here, our null is there's no difference in snack number, while the alternative is there really is a difference. I have no background information here, so I'll guess a small effect. And for most G-Power tests, if you actually hover over the effect size box, it'll pop up this box here that'll give you effect size convention. So I guess a small effect, so the number is going to be 0.20. Just like two-tail, because I only care if there's a difference. Doesn't matter if old persons have higher number of snacks or young persons have higher number of snacks, just a difference. So with that, it'll spit out a total sample size of 912, and since they were equal groups, 456 per group. Old persons, young persons. Here are 3 practice for the Mann-Whitney. Take some time to try these yourself on average number of walks, average number of meals, and average number of weight loss websites visited per day. So for the first question, we're given standard deviation, given means, and it looks like there's an equal number of young and old persons, so we'll have an allocation ratio of 1. Get effect size with that mean and standard deviation information. I'll go with a min-ARE distribution to be conservative. We we find a total sample size of 6, 3 for each. Question 2, we're given the raw data to calculate our own means and standard deviations to get an effect size of 0.53. We'll try a logistic distribution, that's what I did, an allocation ratio because these group sizes were equal, to get a total sample size of 82. Then the third question gives no information, so I try a medium effect, logistic regression, then use two-tailed, and an allocation ratio of 1, because I have no reason to believe that they'd be different group sizes, to get a total of 118, 59 each. Next, we have the paired t-test. This tests if there's a difference in means between two groups, but the groups are paired. They're dependent. This is often things like leaves on the same branch, siblings, the same individual before and after a treatment. Like, for example, a patient being measured for heart rate before a run and after a run. Do this in G-power. Now it's means difference from two dependent means matched. Tails, alpha, power. You're going to enter means and standard deviation for groups if you have background information. Now the additional thing, as opposed to the two means, is you actually have to enter the correlation between groups. Then hit calculate and get total sample size. Naive, A through C, guess effects, and calculate. Is heart rate higher in patients after a run compared to before a run? The null here would be there is no difference, so the mean difference is 0, whereas the alternative is that it's higher than 0. I get trial data to get means and standard deviations, and also a correlation of 0.34. Enter all that into the group parameters to get a large effect size, and I put a single tail. Now, if we would just have mean differences, we can actually use the from differences option rather than the from group parameters. And a rule of thumb for correlation, if you don't have any information on it, 0.5 is a good kind of default or standard. We find here that the total sample size is 4, which means 4 individuals, each with a before and after measurement. So we see here that this is a very large effect size, so it really didn't need very many samples at all. Here are 3 practice examples. Take some time. For the first, on heart rate, we're given information in raw data form, so we can get means, standard deviations, and also correlation. We have a very high correlation between the two of them. To get an effect size of 1.66, and since I'm looking about higher, I'll use a one-tailed test to get a sample size of 4 pairs. For the second, for metabolic rate in patients, what we're given is actually a mean difference with a standard deviation, so we can use that mean differences calculation to get an effect size of 0.25, and two-tailed, because we're actually about difference, a sample size of 126. For the third, we're given no information, so I guess a small effect and a one-tailed test, because it's lower, to get a sample size of 156. Finally, we have the paired Wilcoxon, the non-parametric version of the paired t-test. You can answer questions like, are genome methylation patterns different between identical twins? To do this in G-power means Wilcoxon sign rank test under t-tests, 1 and 2 tails, parent distribution like the 2 means Mann-Whitney, power alpha, like in the paired t-test, you'll need to have correlation in addition to mean and standard deviation. And if you don't have any background information, you would just guess this. So, are genome methylation patterns different between identical twins? Here I would set the null as 0% difference and the alternative as greater than 0. Select one tail because it doesn't make sense to have negative methylation. I have no background information, so I'm going to select guess a effect size that's small, and this gives me a total sample size of 181. So this is going to be 181 pairs of twins, or 362 individuals total. Here are 3 examples for the paired Wilcoxon on methylation patterns in fraternal twins compared to birth order, and then cancer risk in identical twins. The results of the first question were given the mean information, so we can plug that in. And we don't have correlation, so let's just do the default of 0.5. We get an effect size of 0.89 with two-tailed, and the min ARE, we get a sample size of 14 pairs. For the second, we're giving the raw data on difference. So we can use the mean differences to get an effect size of 1.33. And again, I will use the min ARE with no other information to get a total sample size of 6 pairs. And finally, we're giving really no information at all, so I'm going to guess a small effect, guess a min ARE, and use a one-tailed test because we're asking if it's lower to get a total sample size of 181 pairs. So this concludes the first segment of tests, the t-tests. We will pick up next segment with ANOVA. Thank you.